All right, welcome back everyone. In this section what we're going to talk about is a brief overview of concrete. I'm assuming some of this might be review from Con 151, but still some important stuff to know anyway, so let's get on with it. When we look at our concrete components, there's a couple different ingredients that are very important. Making up the largest percentage are our aggregates, meaning our sand and gravel, where gravel is our coarse aggregate, sand is our fine aggregate. We also have water and cement. So water is 14 to 21%. Cement, even though people tend to mix up the words concrete and cement, hopefully you can keep them straight, cement only takes up 7 to 15% of the total proportion. So really it's one of the smaller ingredients. Air 1 to 8%, and admixtures would be this little extra leftover bit that we can add to change the consistency, the workability, quickness that our concrete sets up, things like that. So let's start this by looking at each one of those components, starting with aggregates. When we look at these aggregates, what we really want is a well-sorted aggregate. So we have really coarse material all the way down to our fines, right? If we can have that good gradation, then it fills up all the voids a lot better. What aggregates do, or what they'll affect based on this gradation, is it'll affect the weight and the stiffness of our concrete. And we know about modulus elasticity, we talked about that before. That was our slope, our rise over run, if we were to look at a stress strain diagram. So it's much steeper, or the aggregates can affect the steepness of that concrete, right? Concrete strength is based on the paste aggregate bond. So if you think about concrete and you have all those chunks in here, in between all of our aggregate is our cement paste. And the more aggregate, well, we'll talk more about aggregate and paste in just a second. Also, it affects the durability. So aggregate's one of the most important things as far as our total concrete mix. When we talk about this aggregate, there's really two different shapes. We can either have a rounded shape or an angular shape, and you might be able to imagine how that whole thing could bind together. If it's rounded, it would be more fluid, like less bound together, so better workability. If it's angular, those sharp angles would make it less workable but stronger as far as our bond. Same idea with the texture. If it's a rough texture, then you can think about it being rough and grabbing onto that cement, making it a stronger bond, making it a stronger concrete. But if it's a smooth, then it's more workable. So you're always fighting those two characteristics. So here's an overview of what I just said. If it's round, we have low strength but high workability. Paste requirement just means how much of that cement paste am I going to have. Angular, high strength, low workability. Rough, high strength, low workability. Smooth, low strength, high workability. So the next ingredient would be the cement, locking in those aggregates together. The primary cement that we talk about is Portland cement. Now that's not a brand name, but it's a type of cement. It comes in this powder, like this bag. Now when we did our lab, we used a pre-mixed concrete, so it had cement and the aggregate already all mixed together, right? This is the glue that holds the concrete together, backbone of the concrete mixture, and it is hydraulic. And hydraulic means that as soon as it comes in contact with water, that's when the chemical reaction occurs. Because it's a chemical reaction, it can actually take place underwater. It's not a drying out, it's actually all chemical reactions, so important to remember. When we talk about this cement, there's 5 types. Type 1 is our normal, most basic cement, general purpose. You'd see this on like interior walls and almost any other type of concrete. That's what we actually used for our lab. Type 2 has sulfate resistance, but it's just moderate sulfate resistance, because type 5 is high sulfate resistance. So 2 and 5 go together depending on how much sulfate resistance you need. If you don't remember, if we have sulfate and it's in our concrete's exposed to it, it'll eat away the concrete. So we need to resist that with the type 2 or type 5 Portland cement. And that's why it says for box culverts or foundations or piers, things that are under the ground where it can be exposed to high concentrations of sulfate. Type 3 is high early strength, so of course you got to be quick because it's going to set up quickly, and this is used on like highway projects where you're just pouring and you're working your way down along. You don't have 28 days to keep going, right? Type 4, we have a low heat of hydration. So when we have a massive structure like a dam, then we have too much heat and we have to deal with all the issues with all that excess heat coming off our concrete, so we could use a type 4 low heat of hydration. So let's move on to the air in the concrete. There's two types of air that can be in your concrete. One is entrapped and one is entrained. Entrapped air is that unintentional, when you're mixing it all up, you're introducing this air, right? That's why we use our internal and external vibrators to try and get out those little air pockets, because those are the unintentional air pockets, and they can be irregular shaped, have large volume, and of course it decreases the strength, because if you think about concrete pushing down, you have a big air pocket down here, and the compression just isn't there. You've decreased your cross-sectional area in a way, right? However, we do want some air in our concrete. Remember, it was one of those fundamental ingredients. So that type of air is called entrained air. So that's intentional, meaning we've added that air to our concrete. So this is usually in the form of some sort of admixture. It could be a special cement or cement mixture. Now these are spherical and small. Think air bubbles, right? So if you've ever seen the reaction when you put this admixture into concrete, it's basically like just starts bubbling, and those bubbles are spherical by nature, right? And this is why we want it, because it improves the durability and decreases that internal stresses, because it gives area for the concrete to move into, if it feels like a stress in one direction, it can move a little bit in that direction. So think about freezing and thawing. If you get any water in your concrete and it freezes, it's going to put those pressures. Well, the air is like a shock absorber, which will allow it to freeze and thaw. So what does air do in essence? Well, it does increase the workability. So more air, it's easier to work with, it's easier to form, to get it into all the voids and places where you need it to get. Also the screeding, troweling on top, things like that. However, what happens is our strength will decrease as I add more air. Our durability will increase for the reasons we just said, to allow that freeze and thaw. And of course our unit weight decreases because we've changed the density by adding more air, right? So the weight of our concrete changes. So we can talk about cement hydration. So what is hydration? That's that chemical reaction, that process between water and cement. And this is what actually produces that hardened concrete, right? And this starts as soon as the water comes in contact with our cement particles. The hydration process sets in, and we only have so long to work with it. Now we can add admixtures like retarders, which would slow down that hydration process, so we have more time to set our concrete. And we can also have accelerators, so it can actually quicken the process, right? Hydration is an exothermic reaction. That means it's producing heat, right? And this is called the heat of hydration. So if you've mixed concrete, we've mixed concrete in the lab, right after you mixed it and you put it in your containers, if you were to fill the containers, you'd feel heat, a little bit more if we were to wait a little longer. And the extent to which hydration is completed affects the strength, durability, and the density of the concrete. So we want full hydration, meaning we need enough water to have the full process take place. And here you can see the process where we have our cement particles, and then we have our water is coming in, and our water starts to form all around each one of these cement particles. And if we have complete hydration, what that means is we don't have these voids that I see right here. I mean, this is still an intermediate step, but if it were to finish and I had those voids there, it meant we didn't have enough water, right? So that's what it means why we want 100% hydration. And here we can see either a unhydrated cement particles versus the hydrated cement particles. And I can see this piece of aggregate right here that's just sitting there. And what's the bonding on there? Well, there's a couple little pieces of that cement reaction, but not enough to make a true bond. What we want is it to be fully encapsulated by that cement, by the cement particles. And so one of the factors that contributes to this is the size of our particles. If we have finer particles, then we have a greater area, surface area, that is exposed to the water. So that means that we have more rapid formation of that gel-like cement and water consistency. The rate of hydration is increased, so the whole process is going quicker when I have these finer particles. The rate of strength gain is increased, so I actually have the faster and stronger. and the setting time is shortened. And we can see some comparisons here for 1, 2, and 3 centimeter cubes to get an idea of some numbers there. So like I said, this heat of hydration, while this chemical reaction is happening, it's producing heat. And I can see this, it massively produces heat over that first like 15 minutes, and then it kind of just cools off and is just a normal temperature, room temperature, well, slightly more than room temperature. And then it comes along and it heats up again after like say 20 hours or so, and then eventually it goes back down to its lower heat of hydration. But the heat is given off right at the beginning when you mix it, and after about 20 hours. So we did this in our lab. You should be very familiar with it, but just to cover it, slump testing, we have a slump cone, we have our rod, and remember this slump test, what was the purpose of it? It's a rough measure of the consistency of concrete, and basically what it, more than anything else, especially for our lab, it measures that water to cement ratio. The higher the water, the higher the slump. So this does say it can be changes in water content, mix proportions. For our lab, all the mix, they're pre-mixed except for the water, but if you had different aggregate in there, less aggregate, you'd have more slump, things like that. Also any characteristics of the materials. For instance, if I were to put in a super plasticizer, which makes it more workable, of course I'd have a much higher slump, right? The process, I don't want to go over this too much because we've done it, right? Put the cone upside down, put it 1/3 of the way full, tamp it 25 times, put it 2/3 full, tamp it 25 times, fill it to the top, tamp it, flip it over, and then this is your slump, of course, your distance that it goes down. It should be from the bottom of this rod technically, right, if you're being really accurate. So what is the relationship between slump and water cement ratio? We tried to have a very low water cement ratio for one of our groups where we should have a slump of only 0 to 1 inches. More the medium stuff is like 2 to 5.5, and then the sloppy high is like 7 to 10. Of course you have stiff and wet in between for those intermediaries, but for our lab those are the 3 that we did. So let's move on to the strength of concrete in general. Concrete is very strong in compression. That's its primary characteristic. Not tension, not bending, not torsion, just compression. We have, and that's how we always rate it, right? So if we say F prime C, if you haven't seen F prime C, what that means is the compressive stress. And what this is saying for low strength concrete, we'd have a compressive stress less than 3,000 pounds per square inch. For normal strength concrete, we would be between 3,000 and 6,000. That's most typically what we're dealing with. I'd say usually between 4,000 and 5,000 is most common. High strength is between 6 and 12. It's very dry usually. It may have some other additives, and you're probably using that high strength cement. You can have very high strength with a compressive stress. It should be a lowercase f. Greater than 12,000 psi. So very special projects if you're using that high strength concrete. Very high strength concrete. And we've done this before. We've talked about the compression test with our molds. We've done this. You should have put it in your cylinder the same way we did it in our slump cone where you're rodding it. You have 3 layers, and we're testing on the 28th day. Now, at the 28th day, we should have 98% of the total strength of our concrete, at least whatever is prescribed. So if you were actually determining, if you were given a requirement for what strength concrete you had, you get a little bit more than that, but that's basically what you're going to base it on after 28 days. And it says you should always make 3 test cores and then take the average. Well, that's what we did, or that's what we're doing in our lab, right? Then we can actually do the compression test. Now this is kind of cool. When you're actually on a site, we want to do a test at least once a day, but not less than 1 test for each 150 cubic yards of concrete. Meaning if I have a lot of concrete and I'm placing it every so often, every 150 cubic yards, I'm going to need to take a test. So if I'm doing more than, say, 150 in a day, maybe 300 in a day, I would need to do 2 tests in that one day. Otherwise it would just be 1 a day, right? If we look at the maximum stress, PSI is calculated from the maximum load known and the cylinder area. That's because our stress, as we remember before for compressive stress, is just the force over the area. So if we have, like, say, a 4,000 PSI concrete, and we're going to put it in that testing machine, we could figure out what kind of area we would need, because we could do pi over 4 times, for our cylinders that we used were 4 inches squared. Solve for P, and you'd find out P is equal to, so solving that, we end up with an overall force of about 50,000 pounds, or we could say P is equal to 50 kips, right? So when we test our cylinders in the lab, since that concrete bag should have made about 4,000 psi concrete, we would expect to be about 50,000 pounds. That's heavy, but that's what it should take to break those cylinders. If it's less than that, it's probably because of our method of placing it in the cylinders, too much air, something like that. So let's move on to flexural strength. We talked about flexural strength last time, right? Where we said if something's bending, at least if I have a force up top, not a cantilever, everything would flip, but a force on top, we make a smiley face. The top is in compression, the bottom is in tension. And that's what we see in this slide right here. Where the top is crushing and because it's being pushed in compression, the bottom is cracking because it's being pulled in tension. So if we were to look at the stress profile, this is the same profile similar to what we saw before. We have compression and we have tension. In between, it's linear. But what it means is we have all tension on the lower half, all compression on the upper half. Well, what we said is concrete is really weak in tension. So what we end up with is a crack on the bottom of our concrete because it can handle the compression, but it can't handle that tension. And once it cracks, if we don't have any reinforcing or anything, of course, it'll fail. So what we can do is add steel reinforcing, aka rebar, right? And you can see this has 3 bars in here. We didn't really talk too much about bars, but hopefully you remember from like from 151, if I had a 3/8 inch rebar, that's called a number 3, so it's always that number over 8, right? So with that in mind, now let's look at our structural profile. I have the same triangular shape when it comes to the compression, but look at this lower half. I have replaced that lower triangle with just this single force. So this is how we design reinforced concrete, is we assume this whole upper part, the compression part, is 100% being supported by the concrete. The tensile part down here is 100% being handled by the steel. And they should be balanced out in order to have this beam stable. So all tensile forces are transformed from the concrete to the steel, and yielding gives warning to failure. So this is a big part of engineering this stuff, because if I go back and said, why not design this thing and put a whole bunch of steel in here, right? Instead of just like 3 bars, we'll put like 30 bars down here and make it super, super strong. The problem with that is once it starts to get loaded, if it overloads, if you overload your beam, the top just crushes and the whole beam comes down. You have complete failure. So instead what we want is for it, the steel, remember our stress strain diagram for steel. It went up and then it had this big elastic part, right? Our plastic part, which means steel can bend and stretch. Well, that would happen if this started to fail. You can imagine the steel is stretching, so the concrete can't stretch, so it starts cracking every which way, but the steel just stretches. Well, it doesn't fail, it just keeps stretching, especially if we still have this strain hardening bit in here, right? So that keeps us from having a total failure. Location of the reinforcements is critical to strength and behavior, of course, and reinforcement can be pre-stressed. So what do we mean by pre-stressed? What we're talking about here is there's 2 types of pre-stressing, and this kind of fools some people because we have one that's pre-tensioning. Well, pre and pre, that's good, but we have one that's post-tensioning. So even though it's pre-stressing, we can have post-tensioning. Why the difference? Pre-stressing means before we add any loads to our beam or structure. So that's what the pre means. Stressing means we're just pulling it. We're adding a tension into our steel, right? And we can either do it before we pour our concrete. That's pre-tensioning. So in that case, we stretch our bar here, our steel. we pour our concrete, and once we pour our concrete, we release these jacks, and the whole thing sucks together, right? Making this whole bottom pushing on this concrete. And in essence, what you'll end up with is we have our initial, from the loading, this is from the load, we have our concrete profile for stress and strain. Well, what this is doing, it says, well, now we're just going to put the whole thing in compression due to this pre-tensioning or post-tensioning. Well, I can add those two together. And if I add them together, I end up with something where the top is way more compressed, but in essence, the whole beam is in compression through its profile. So we don't have a tension region because it's sucking the whole thing together. That's a little bit more than what we really need to know, but this should say equals. A little more than what we need to know, but that's kind of background information between this pre-stressing and post-tensioning. So I talked about pre-tensioning. What about post-tensioning? Well, that means I have ductwork poured into my concrete. After the fact, I put a tendon in here, and I jack it tight, and there's always going to be an anchor holding it tight. One advantage to this post-tensioning is I can actually go back and adjust and add more tension to it for whatever reason, right? Where this one's cast into the concrete, so it's not adjustable. But also, this one could fail by the anchors. This one doesn't have any anchors. So there's advantages and disadvantages to both. So this is an overview. I think we talked about everything. Adding high strength reinforcing tendons and pre-stressing, applying tension to the steel before concrete sets. And of course, the concrete is permanently bonded to the tendons, and it adds that camber. And then the idea is that once it's in service, then the loading on this beam will make it so that it'll be, back down to square, back down to level. Most commonly used for building girders, T-beams, some columns. And here we see the process. I can see that camber is put in once the load comes along. It flattens out. Versus post-tensioning, you can see there's these ducts in here, right? And I have this tendon that is put through that duct that I'm pulling on, or on a slab, same idea. And I'm using like a jack to pull the whole thing close. And this is most common on like precast slabs or girders or beams, things like that. All right, so as usual, I hope you found that informative. And let me know if you have any questions or comments, and I'll talk to you all later. Thanks.